Hello everyone and welcome back. In the last video, we explored recurrent neural networks, LSTMs and stacked LSTMs. What we understood was that to get the context or to predict the next word that will occur in a sentence, to actually predict a sentence or write a sentence by a model itself needs an LSTM model. Next, we'll be trying to use some pre-trained embeddings that are already available in TensorFlow Hub, and we'll call them up with RNNs and see if the training accuracy as well as validation accuracy of our dataset that we've been working on increases or decreases or remains the same. So let's just go ahead and explore pre-trained embeddings with RNNs. In the previous examples, we gathered the full set of words to be used in training set, then trained embeddings with them. These were initially aggregated before being fed into a dense network. And in this chapter, we explored how to improve the results using RNNs. While doing this, you were restricted to words in your dataset and how embeddings could be learned using the labels from that dataset. So usually when do we use a pre-trained model or a pre-trained embedding is when the dataset that we have is very small, or we feel that it is not good enough for our training or our validation accuracy to go above our training accuracy. So in the scenarios where we feel that we are trying our best of regularizing the parameters and tuning the hyperparameters, but somehow the overfitting is not removing, it's not reducing to the extent we want. So we can use pre-trained embeddings there, which are already trained on much larger data set compared to ours. So when we think back to chapter 4, we explored transfer learning, and what if instead of learning the embeddings for yourself, you could instead use pre-learned embeddings where researchers have already done the hard work for you. So in this one, we are using GLOVE, that is short for Global Vectors for Word Representation Model. It was developed by Jeffrey Pennington, Richard Schockler, and Christopher Manning at Stanford. So in this case, the researchers have shared their pre-trained word vectors for a variety of datasets. A 6 billion token, 400,000 words, a set in 50, 100, 200, and 300 dimensions with words taken from Wikipedia and GigaWords. So you can see that in this there are a variety of datasets that our embedding was pre-trained on. So I won't be going through this whole lot of billion and around 4 to 42 to 6 and 840 billion tokens that are explored here. But we can say in brief that the datasets or the variety of datasets are pre-trained embedding has been trained upon comes from Wikipedia, GigaWord, Common Crawl, and Twitter Crawl of 2 billion tweets. So it's a lot of data, to be short. Given that the vectors are already pre-trained, it's simple to reuse them in your TensorFlow code instead of learning from scratch. First, you'll have to download the GLOVE data. So they've opted to use Twitter data with 27 billion tokens and 1.2 million word vocab. So it's a huge vocab. And then download is an archive with 25, 50, 100, and 200 dimensions. To make it little easier, so they have hosted it on a 25 dimension version near this code, in this code. So it's a zip file, you can just get it and you unzip it to use it. So this whole code here is to just unzip it using OS and zip file. So we are opening it and we are reading it, then we are extracting all the information and finally closing the zip file. Each entry in the file is a word followed by dimensional coefficients that were learned for it. The easiest way to use this is to create a dictionary where key is the word and the values are the embeddings. So the code goes like this: glove underscore embeddings equals dictionary. So we are just using a dictionary to extract all the information and use the information in a easier way. Right, so we are opening the txt file that we got, and for line in F, we just split it, then values from 0, np as array values, we just get the values, coefficients, and then we just close the file. At this point, you will be able to look up the set of coefficients for any word simply by using it as a key. So if you have like a word called frog, then you can simply say glove underscore embeddings of frog, and you will get the word. And because you'll get the coefficients because you're using the word as the key, right? With this resource in hand, you can use tokenizer to get word index for your corpus as before, but now you can create a new matrix which I'll call the embedding matrix. So this will use the glove set embeddings taken from glove embeddings as its value if you examine the word in the word index of your dataset like this. So this is the word index of the dataset. Like we have already done this in before, in the previous videos, we have already seen how a word index looks like. So each word has its own value and given to it. So it's called a word index, right? Then the first row in the embedding matrix should be the coefficients from glove or for OV. The next row will be the coefficient for new and so on. Right, so instead of having the word index like this, we're having in form of a matrix. That's simple. So converting that into a matrix and creating a matrix, what we're going to do is we are going to initialize a matrix with np.zeros, vocab size and embedding dimensions as parameters. And then for word or in an index in tokenizer.word index.items, because it has word index and we want to call word index. So if index is greater than vocab size minus 1, then you break it. Otherwise, embedding underscore vector equals glove embedding dot get word, and you get the word that you have to put in the embedding vector there. So if it's equal to none, then you just take the index of the vector, that's the index for the matrix, and you put the word in the same index, right? It's just simple matrix function how you do it. It's just complicated because we are working with a much complex word index here, right? So this simply creates a matrix with dimensions of your desired vocab size and the embedding dimension. Then for every item in tokenizer's word index, you look up to the coefficients for glove embeddings and add those values to the matrix. You then amend the embedding layers, so you to use pre-trained embeddings. So you just don't need to do anything. In just the embedding layer, you change the weights equals to embedding matrix and trainable equals false, right? So that's how you just get the trainables. You have to set the trainable equals false because you don't want to train it on your own weights. You need to use the weights that it has been trained upon before, right? So you can now train it as before. However, you will want to consider your cap size. One of the optimizations you did in the previous chapter to avoid overfitting was intended to prevent embeddings becoming overburdened with learning low frequency words. You avoided overfitting by using smaller vocabulary of frequently used words. In this case, the word embeddings have already been learned for you with glove. You can expand the vocabulary, but by how much? So, when coming to expanding the vocabulary, first thing to explore is how many of the words in the corpus are actually in glove set. So it has 1.2 million words, so there is no guarantee that it has all the words. So it all of your words that you have in your corpus. So it's a big number, 1.2 million, but still there is no guarantee, right? So Here's some code to perform a quick comparison so you can explore how large a vocab should be. Let's first sort the data out. So create a list x's and y's where x is the word index and y equals 1 if the word is in the embeddings or 0 if it isn't, right? Additionally, you can create a culminative set where you count the quotient of words at every time step. For example, the word OOV at index 0 isn't in glove, so its culminative y would be 0, right? The word new at the next index is in glove, so its culminative y would be zero point 0.5. That is, half of the words seen so far are in glove, and you'd continue to count that way for the entire data set. So it's a basic simple code to sort the data out. So we have x's, y's and culminative x and y and total y equals 0. So we're using tokenizer.wordIndex.items, append index into x and culminative of x.append index. So if the glove embedding dot get word is not none, means it is present in the embedding. So total of y is added with 1, right? And you append 1 to ys. Else you append 0 and culminative y dot append would be total of y by index. When then you plot the x's against the y's with this code, so you import matplotlib.pyplot as you already used to plot the graph for x and y's. So you just give the subplots, the ax.spines of top dot set visible false, and you plot the margins for x is 0, y is none, tight equals true, and you fill with ys. So the chart would look something like this. So you can see the frequency, and in the middle somewhere the frequency is actually changing. As you can see in the chart, the density changes somewhere between 10,000 and 15,000. This gives you an eyeball check that somewhere around the token 13,000, the frequency of words that are not in the glove embedding starts to outpace those that are. So you can see that from 0 to around 13,000, the lines are densely packed. So we can see the frequency is high, but some around 13,000 and uh, till the end of the chart, you can see the frequency is distributed, right? So if you plot the culminative x against the culminative y, you can get a better sense of this. Here's the code for that. So you just plot it using matplotlib. So plt.plot culminative and the x's that you find here. You can see you cannot tweak the parameters in the plt.axis to zoom in to find the inflection point where the words not present in glove begin to outpace those that are in glove. This is a good starting point for you to set the size of your vocabulary. So you can see that the frequency of words against word index against glove, right? Using this method, I chose to use a vocabulary size of 13,200 instead of 2,000 that was previously used to avoid overfitting. This model architecture where the embedding dimension is 25 because glove set I am using. So the code is here. It's almost the same. It's nothing much different. You have already done this thing. We have the model with the embedding layer as first, trainable equals false, weights are from embedding matrix, then you have a bidirectional LSTM layer, two of them actually, and then a dense layer followed by another dense layer with one neuron in the end, right? Then you have Adam. We have not using the default ones. We have defined the learning rate, and then we use model.compile. It's all the same. Training this for 30 epochs yields some excellent results. So you can see the accuracy here. So you can see actually accuracy and validation accuracy are actually pretty close to each other, and you can see This is pretty good accuracy for stacked LSTMs. This is reinforced by the loss curves shown in figure 20. The validation losses no longer diverges, showing that although our accuracy is only 73%, we can be confident the model is accurate to that degree. You can see the accuracy is around 73%, but it is pretty good. We don't see much overfitting at all. Right? The training the model for longer shows very similar results. So you can see for this one, both our validation and training loss are going down, and it's about time that the training model for longer shows very similar results and indicates that while overfitting begins to occur right around epoch 80, the model is still very stable. So there is some kind of overfitting still now, but it is not of that margin that we cannot decrease it, right? And the accuracy is pretty well as well. So you can see the model still fits well here for 150 epochs. Yeah. So this tells us the model is good candidate for early stopping. So for 100 epochs, the lines were almost parallel. For 150, the margin is beginning to increase. So that's where we can use early stopping at around 75 or 80, right, epochs. So there we've got kind of good results. So he's tried the onion source for stochastic headlines in sarcasm dataset against other sentences, and like the test sentence was, it was for medical reasons, says doctor to Boris Johnson, explaining why they had to give him haircut. So these are 3-4 sentences, test sentences, and you can see the results are pretty good for sarcastic. So if the values are pretty close to 50% as considered neutral, or close to 0 non-sarcastic, and close to 1 for sarcasm. So like the first value is 0.8170955, so it's almost 1, you can say it's sarcastic, while the next value 0.087, it's almost 0, so you can see that it is non-sarcastic, and somewhere near to 0.5 it's kind of neutral for the third one. So this is it, and we have reached the summary of this chapter. So in this chapter, we introduced you to recurrent neural networks, which use sequence-oriented logic in their design and can help you understand the sentiment of sentences based not only on the words they contain, but also in the order in which they appear. So we saw the basics of RNN, the basics of LSTMs, stacked LSTMs, and how we can preserve the context of text for a long time. We also analyzed some pre-trained embeddings using transfer learning. So in chapter 8, we'll be understanding how to explore and how to predict words. And from there, we'll be able to create a model that creates text and writing poetry for you. So till then, stay with us. Check out the code in the GitHub, and the link would be in the description. For any problems or any questions or queries, do write us in the comments or reach out to us on our Twitter handle. Thank you so much and keep learning.